Okay, what I'm going to do today is I'm going to look at circle theorems. Now, circle theorems, more advanced angles within circles, and there's different stated results or theorems which relate to these. Okay, before I start that, let's just look at some basics of lines within circles. If I draw a circle on the board, the best I can there, O being the origin, the centre, and I draw various lines on there. Okay, now that one there, call it number 1, is what you set your compass at to draw the circle. So it's the same distance from the centre to the outside of the circle, its circumference remains the same. Number 1 is called the radius. If you go right across through the centre to both ends of the circumference there, you can see there you've got 2 radiuses, and that is given the name diameter. So number 2, call that number 2 there. Number 2 is given the name diameter. If I now look at a line which doesn't go through the centre but touches both ends of the circumference, okay, now I'll call that number 3, that's actually called a chord. Number 3 equals chord. Now a diameter is actually a chord, a special type of a chord which goes through the centre of the circle. So there's the 2 linked, that's just a special version of number 3. Number 4, let me just get my red pen here. If I go it's not drawn very well, it's meant to be curved there, call that number 4 there. If you go back to there, number 4, that's part of the way around the whole circle, that's called an arc, A-R-C. If I call number 5, now I'll just point to 5, now 5 is all the way around the circle, okay? That's the actual perimeter of the circle, and it's given the name circumference. It's actually the curved part of the circle, okay? So that's given the word circumference. And then lastly, this could be any position, let's say, shall I draw that there? Let's say I've got a line touching the circle in one place, let's say it's touching it about there, okay, call that number 6. That is given the name tangent. A tangent is a line which touches, well, a curve actually, but in this case I'm talking about circles, touches the circle in one place, and that's given the name tangent, okay. Obviously there, I'm not going to go into the area part of things, but you can see that diameter there, right across there, number 2, is splitting the circle into 2 halves, and obviously this half a circle is called a semicircle. So that concludes the basics of basics of all the special lines within a circle. Now let's look at all the circle theorem results. Okay, I'll categorise them under rule 1, rule 2, etc. Let's take first one, rule number 1. Okay, now rule 1 number 1 is not really a theorem. It's an obvious thing, but it's a very important one. It's so simple that it's useful with the more sophisticated theorems. If you take a circle again, O as the centre, okay, and I make 2 radii, each one of those there, then what you find out there is those 2 sides are the same. It's not drawn to scale here, which means I've got an isosceles triangle, which means that these 2 angles, called the base angles, of an isosceles triangle are equal. So rule 1 is that the base angles of an isosceles triangle are equal. Very useful result, so simple, but that can help you move around the circle and get other angles very, very quickly. So that's rule number 1. Rule number 2, I'll just move over to this side here. I'll put 2 on the board. Rule 2. Okay, again I draw a circle. There's the centre O. The origin there. And this time, well, I'm going to draw the 2 radii as before. But from these 2 points here, you can see that these 2 points, the further those points get, the distance these points on the circumference, if they alter, they affect the angle at the centre there. So if I now draw 2 lines from there, which are going to be chords, then the theorem is this, linked to this. So if I put that in blue there, that just stands out. We can see that chord there, so that's not chord, sorry, that arc, which is a chord there actually, is making an angle at the centre. okay? But the same arc, the blue arc or the chord here, yeah, from both ends there, is also making an angle at the circumference through these two chords here. And the theorem states that this, if that angle there is A, then this angle here is 2A. Okay, notice how they face each other. So it could be the other way around, that could be the reverse roles, and you have to turn your book around to see it. And therefore the theorem from that one there is angle at the centre, it was the angle at the centre there, angle at the centre is double the angle at the circumference. And that's my second theorem there. So that chord, sorry, not chord, there's a chord there actually. That arc, that blue arc or chord there is making that angle at the centre, is also by virtue of its ends making that angle at the circumference. And the angle made by that arc at the centre is double the angle made by that arc at the circumference. And that's how you would have to give the reasons in the exam. Is not the work, and you have to write these stated theorems out like that, or abbreviate them to that. Okay? So, if I rub those two off, I'll go to rule 3 and 4. Okay? Notice both those theorems I've just used involve the centre. So it's a good idea to categorise those theorems which work with the centre and those which don't. Okay? So, if I now go to, and the reason why I've linked up rule 3 with rule 2, you'll see in a minute. There's this one here. So I now draw that. I'm going to draw a diameter right across there. So there's the diameter. And I'm going to join up here. Okay? Now, this could actually go under rule 2. Okay? Alright. We can see, I'll just put this in colours here. That arc there is making that angle at the centre again. Okay? Actually, what I should have said before, angle made by is another word for that, subtend. So another fancy word, made by, is also goes under the word subtend. So the angle made by that arc at the centre, which you can see there, is 180 degrees because that's on a straight line. Okay, but that same arc is also putting this angle at the circumference here. Now we know from rule number 2 before that the angle made at the angle at the centre, that arc's making that at the centre 180, is double the angle at the circumference, so that's got to be 90. Now that could be rather confusing within a very complex question. So what mathematicians have done is, yes, it is the same as rule number 2, but they give it a different name. So we can all spot half circle, semicircle, and basically, if I drew that half circle, it doesn't matter where this point is here, because coming off that same arc there, you're going to add the same angle made by those two arcs. If I could draw again here, I'll just actually draw that on there. You can see angle made by the arc at the circumference there, sorry, at the centre. Okay, is double the angle made by the same arc at the circumference. That's going to be 90 again there. So what they say is, to abbreviate that, they give it a different name, angle in a semicircle. Okay, angle in a semicircle is equal to 90 degrees. There we are. Okay, from there. And you can obviously see there are loads of 90 degrees that would be there on that one. Rule number 4. Okay. Here's this one. If you take a circle, oh, by the way, I was about to say there, again, that theorem involves the centre again. Some don't, some do. Okay, there's the centre. And let's say I've got a radius and a tangent. Well, they cross at 90 degrees. Actually, it's the diameter as well. If you want to call it its diameter, linked to the radius here, because that's right across. Okay, and that goes under the name here, or reason. I'll write it here. A radius and tangent meet at 90 degrees. Very simple one. Again, it involves the centre on that one. Okay, let me just rub those out. Okay, rule number 5. Okay. Okay, a less familiar rule here, rule 5. Okay, if you take a circle again, okay, and there's the centre, so we're involving the centre here. That line there is a diameter. Okay, if I now draw a chord on here to that diameter here, okay, what would happen here is the rule is there, a diameter bisects that chord at 90 degrees. So it bisects it, so it cuts it into 2 equal parts, hence the dashes mean equal. Okay, and it bisects it at right angles, as you can see there. So that's another result there. That diameter is bisecting that chord at right angles. Okay, so if you drew a chord right across there, it would actually cut it into 2 equal parts. Okay, if I drew, for example, it doesn't have to be there, if I drew the chord here as well, that would still be 90 degrees, and that would be equal. I have to put 2 dashes there, because although they're equal, they're a different length to the other 2 there. Okay, and that goes under the name here, a diameter bisects a chord. Probably less familiar to use this one, bisects a chord at right angles. Okay, rule number 6. Okay, well actually this is sort of linked to that rule, I think it was rule number 2 I was using before, angle at the centre is double the angle at circumference. So rule number 6, if I draw a circle again, not the best circle there, okay. Now, if I draw on here, let's put the blue again for a sort of an arc here, there's the arc, okay. Now, if I draw lots of chords from here, like that, if I keep going off the 2 ends of the arc here, I'll do another one here, what you find out is, use my red pen, is these angles here are all the same. Now I'll use the letter A for angle like I've used before, that. Okay, now, if there was a this doesn't involve the centre, but if there was a centre in here, you could relate this back to rule number 2. Because if I did put a centre in here, which I don't want to put here, okay, if there was a centre there, then the angle at that centre is double the angle at circumference. So this would be, if there was a centre here, that angle there would be 2A, and these are all coming off the same arc, these are all the circumference, so it's actually linked to rule number 6. Now, what do we call that? Alright, well, it's probably hard to see how I've drawn that there, if I can try and put a red line in here. That's meant to be an arc there. You can see there is a chord here as well, a very small chord. Now, what you notice is all the angles which are the same are in the same segment. Yeah, that's one called a large segment or a major segment. This is called a minor segment. So because all those angles are in the same segment, it goes under the name angles in the same segment. Angles in the same segment are equal. Again, that one doesn't involve the centre, although I've used the centre to link up rule number 2, as I've said a few moments ago. Okay, that's 6 rules done. Let's just rub those out. Okay, rule number 7. Okay, rule number 7. Draw another circle. This doesn't involve a centre, so we're careful here. Now I'm drawing a 4-sided shape inside that. Okay, so a 4-sided shape there. Okay, let's check on that one there. Okay, if I call these angles A, let's call that B, C and D, then this is a rather special type of quadrilateral because the 4 corners, vertices, are all touching the circumference of a circle. So it's going around the circle and it's given the name cyclic quadrilateral. Okay, so the theorem states that opposite angles of a cyclic quadrilateral add up to 180 degrees, yeah? And that's the rule there we go, opposite angles. You must say the word cyclic in the exam or you will not get the marks for the reason. This is the reasons of the words, the stated theorem. Opposite angles of a cyclic quadrilateral add up to 180 degrees. Okay, important from that. Okay, notice there's no centre on that. Now I could, okay, if I just draw a little mini circle here, I could have drawn one where you could have, I don't know here, there's the centre, I join that up like that, okay, and I've got a quadrilateral again, but that, although those three corners are touching the circumference, that's not, so you cannot say opposite angles add up to 180 degrees because that is not a cyclic quadrilateral, so you can only use what the theorem states. Okay, rule number 8, okay, probably less familiar one here. Actually, I'm going to rub this out. This is going to be a bit more detailed. So rule number 8. Let's just move across here. Let's use the board a bit more, actually. Rule number 8 is this. Well, if I obviously draw a circle again, and what I'm going to do is I'm going to draw two tangents. I'm going to have a point outside the circle called an external point. So if I join them up here, I can actually create two tangents. One here and one here. Whoops, missed it out there. Let's just go a bit further. I'll call that point there. And what the theorem states is, okay, the lengths of these tangents from that external point to where it hits the circle are equal in length. So that would be equal. Okay, so the theorem states that the length of tangents from an external point, the lengths of tangents from an external point to a circle are equal in length. I've seen this theorem being used in more advanced questions on Oxford, Cambridge papers with more detailed angle questions, and that little theorem there helps out, definitely. Now, that's it. I can add to that though. That didn't involve the centre, but if I was to put a centre on there, then lots of other theorems come into place here. Okay, if I join that up, one of the theorems I mentioned earlier, a tangent and radius cross at 90 degrees, so I can put 90 on there. I've got 90 on here. Okay, if I just use my red pen here, because let's put some letters on here actually now. So let's call that O, that's A, that's B, and that's C. Then we've got various things going off in here. They're equal, because that's from the theorem we've just used on Rule 8, but these are both equal here, so I put two lines to mean they're equal, the two lines being a different pair of equal sides, because they're both what you set your compass at to draw the circle. So you get that, and then what you notice is you've got a rather special quadrilateral. It's actually OABC is a kite. Okay? Now, a kite as a line of symmetry here. Now, adjacent sides, that means adjacent means next to or equal. Adjacent sides are equal. So this line going down here is actually a line of symmetry. Actually, not a bit further than that, because what I could draw on here is I could go A to C and draw a chord. Now, if I was to extend that line, let's just move the O there, and extend that line there, that goes back to one of the other theorems I said earlier, that, okay, a diameter bisects a chord into right angles. So therefore, from that, I can now say use red here. These are another pair of equal sides here, and this is definitely 90 degrees, because I said a diameter, which is a diameter there, bisects that chord at 90 degrees. And then what you see is you've got lots of things that you can use. You know that the angles in a quadrilateral, that kind, add up to 360 degrees. And then if I just put an extra letter on here and put D, then I've got three pairs of congruent triangles. Congruent triangles, exactly the same shape and size. For example, this triangle here, OAD, is congruent to OCD. The triangle ADB is identical, congruent to BDC. And then the big triangle OAB, which is right angle here, OAB, is congruent to OCB. So you've got three pairs of congruent triangles, and there's lots of things going on there. That's the brilliant thing about mathematics. You start to open up the door to lots of other areas, and all the rules come together. Okay, that's rule number 8. 2 more to go. Very important one now. Okay, one a higher level one. So I'll just draw this on the board. Okay. Now I have got here. Okay, this doesn't involve. Oh, it does involve the centre. Yes, it does. Well, for convenience, I'm going to draw a tangent on the bottom here. If it was it could be anywhere along there. I'll have to spin my book around to see it. Now, what I've got there, if I draw a chord there, okay, and then draw various different chords here, okay, I'll use 2 different colours here. What they found was this: if I go from this side here, that angle there, okay, in blue, okay, there it is, the blue bit there, is the same as the blue bit there. Okay, what it's saying is, and I can abbreviate this theorem actually, the angle made, I'll put it in a long word, you don't really use it as an exam, this is too long to write down as the reason. The angle made by that tangent and that chord is the same as the angle made by that chord at the circumference. Okay, that's not meant to be a diameter there, it doesn't have to go through the centre by the way, it doesn't have to involve the centre here. Okay, if I reverse the process and look at it from the other side, then it's the same thing again. Okay, if I call that red, then this will be red over here. And by the same argument or the word of reason I've just used, the angle made by this tangent, which is the same tangent, with this chord now, which is a different chord, is the same as the angle made by that chord at the circumference. Okay? Alright, so you can see that. Very important, very powerful theorem there being used. Now, what name is it given? Well, it's not. If you notice that, let's take the blue angles. The blue angle is in this segment here. Okay? The angle which is there. Now, it's actually not quite in that segment because it's off the tangent there, but it's good enough as approximation. This other blue angle is in this other segment. And we call it the alternate segment theorem. Yeah? Alternates the angle in one angle in one segment is equal to the other in the other. So we call it, and the same here, if you look at that one there, that's in that small segment, roughly, I know it's slightly out there, and the red angle's in this big segment here. Okay, just to add to what I said there, the word segment, by the way, I didn't bring that in there. If you take a chord, right, and you cut it off here, this area there is obviously not a semicircle because it's not half a circle, it's called a segment. Okay, that's called a minor segment because it's the smaller of the 2 segments. Also, it produces a big segment here, which is called a major segment, and the 2 make the full circle together. Okay, so that's not part of that, but and then it's given the name alternate segment theorem rather than say what I've just said before, alternate segment theorem. And then there's one last, that is the very important one that is to be used there. Okay, the last one. Just rub this out now. Not really, I don't think this has been really used, but it's out there and it's certainly on the AQA exam board I'm using, or the exam board, the exam syllabus I'm following. It's on that here, although I certainly haven't used it over the years here. And basically what it says is this: if you take a circle, and again this doesn't involve the centre, okay, and I draw 2 chords, any chords, you can go over the centre if it wants to, like that. If I label that, I'm going to label what I've got in this book here. So if I call that here, so excuse me, just put my glasses on, I can't see here. If I label that PTQ, and the other one here RTS, then what did it say? It's there, if the 2 chords PQ and RS cross at the point T, so it's the crossing point there, that happens to cross here, okay? You find out this result that PT times TQ, so P to T, T to Q, is the same as R to T, the way around here, times by T to S, RT times T to S, or S to T. And that comes out there. Now that's still valid if, if I was to take the case where the external point, or the T, is where they crosses outside the circle, which could happen. So you could have it crossing outside here like this. Okay, there's the T. And if I put Q and P here, and S and R here, They're still crossing, but they're crossing outside the circle. It still holds that, obviously it's where they cross, P to T, there's your P to T here, P to T, okay, because it always goes from the point to where they cross, so P to T times T to Q, there's your P to T there, there's your Q, T to Q there, is the same as going from R to T, which I've got here, there's my R to the T, times by T to S, there's my T to the S, there's my T to the S there, and that still works there. Okay, again, a less familiar one there. And then you've just got to practice questions on that, but that includes all your theorems are there, and it's quite interesting actually putting them together in higher level questions. Obviously it's going to be a higher level exam questions on this, and just working through that. Obviously reasons could be asked of you, so the reasons are like the words are abbreviated there: alternate segment theorem, base angles of an isosceles triangle are equal. Hopefully that you could take that away, practice some questions, and if you were unfamiliar within your lessons or whatever, you're not sure about these theorems, I hope I've tried to explain them the best I can. Thank you very much.